It's my pleasure to introduce Norm MIRI. I'll give a little bit of background. Norm was an undergraduate at Caltech where he met Peter Goldreich and developed a lifelong friendship. Norm did his PhD in Berkeley, where he studied nonlinear dynamics. So despite all of their appearances, he's a world-class nonlinear dynamicist. Norm did a postdoc at Queen Mary. Then he did another postdoc back at Caltech before he moved to CITA, and where he's been ever since. He's done his time as director, and then a little bit more time after that. He's here on the occasion of being inducted into the American Academy of Arts and Sciences. He's also being inducted into the National Academy of Sciences. Personally, I would say that Norm was my sort of principal advisor and collaborator when I was at CITA. It was a lot of fun, and one of the great things about astronomy is you get to maintain these friendships and collaborations over the rest of your career. So, Norm, take it away.
All right. Okay, you can hear me okay? All right, so yes, I do want to talk about recent work, but I haven't been back to Harvard for quite a while. It's fun to be back here and see everybody. And I hope to talk to a lot of you today and tomorrow. I'll be around all day, both days. So I do want to talk about some observations that one of my former sort of students, Andre Vayner, has been doing using JWST. He's been working with Shelley, who was his actual PhD advisor, Shelley Wright, and Reagan Lembaugh Murray, who's currently a graduate student at UC San Diego. And I was working with them quite a bit because I was on sabbatical last year in San Diego. So it's been a lot of fun. So I do want to talk about this object that's shown here in the red with the really elaborate diffraction spikes around it. So let's just get started. So quickly, the outline I'm going to talk about is a little bit about galaxy and AGN phenomenology and feedback. I won't actually talk about the feedback that the object that I'm going to be describing will be experiencing, because it's kind of a complicated, different subject. I want to talk about the physics of what's going on. I'll show you some JWST spectra. I showed you a quick preview of that. And then, because it became pretty apparent, this outflow that we're seeing, I'll show you the blue shifted absorption, is probably just driven by radiation pressure from the really intense infrared radiation from the torus that surrounds the quasar, the actual disk. And then there's some predictions. First of all, if it is radiation driven, which is suggested because of the optical depth that you see towards the thing, then the velocity that you see this wind coming off at should scale in a way that you can test, which is, somebody asked earlier, are we doing further JWST proposals for this? And the answer is yes, to test this prediction. Okay. Let me turn this off for a second. All right, so I'm not sure how I got that far ahead, but okay, there we go. So just a little bit about sort of motivation for this for people who are not just aficionados of quasars and AGN. A lot of people are interested in galaxy formation, and one of the puzzles about galaxy formation is sort of in these couple of plots here. On the left, I'm just showing the number density, essentially, of dark matter halos. It comes out of theory from doing either dark matter simulations or some theory. And the idea is that you can describe it with a Pressure type function where there's at small halo masses, there's a sort of a power law distribution, and there's an exponential cutoff. That's for dark matter halos. But what we see, of course, are galaxies, which are stars in the bottoms of these dark matter halos. At least that's the theory. Okay? And when you look at those, they follow a bit of a different distribution. And that's actually best seen in the next sort of plot, which is showing the same sorts of things, the number density or whatever, of the number of stars and the mass in stars divided by the halo mass. In other words, sort of the star formation efficiency in a given halo. On the left is sort of an old plot from Mosterdal. On the right, a more recent one from somebody who's here, Charlie Conroy, showing that the number of stars that you have, or the mass in stars that you have, is a function of halo mass. So here's the halo mass along the x-axis. And this is the stellar mass divided by the total mass in the halo on both these plots. And the idea is, right, if you live in a halo mass that's of order 10 to the 12, like we think we do in the Milky Way, the stellar mass is some reasonable fraction of the total number of baryons you think you should have in that halo. It's not quite 1, right? That would be, 1/6 of the halo mass is in baryons. So that's this MB here. This stellar mass never quite gets that high. The efficiency, there's a lot of gas in the halos as opposed to stars. But the reason people are interested in quasars in particular is because, on this low mass end, the efficiency of making stars is very low, and the usual excuse for that is that supernovae prevent you from making a lot more stars. They blow gas out of the galaxy and things like that. On this side, the supernova can't do that job, so you need something else to prevent star formation from happening. One way to do it is to use a quasar. So the feedback from quasars is often used to explain the decrease here on the high mass end. Okay, so that's sort of the motivation for thinking about feedback from quasars. There's different kinds of feedback, which I won't go into in great detail. And the really big halos out here, it's pretty clearly radio jets. But in this sort of intermediate mass, people think it actually has to do with the active quasar phase. Okay, this is another plot showing the same sort of motivation. There's a relationship between the mass in a black hole. I'm having a hard time with this thing here. The button's pretty small. As a function of the stellar mass or as a function of the dispersion in the galaxy. So the M sigma relation, or this used to be called the Magorian relation. I forget what people call it now. Halo mass, black hole mass relationship. And so obviously the galaxy and the black hole seem to know something about each other. And again, one possible explanation for this is that the feedback from the AGN, the effect of the AGN on the host galaxy is what sets this relationship. I don't think that's actually true, but that is one of the motivations. So what kind of forms of feedback are there? The ones I'm kind of interested in are outflows. That's because when people do simulations, the typical types of feedback they do for really massive halos, as I said, they'll use radio jets. But radio jets are actually not all that common. So the other one people use is quasar winds. Okay, broad absorption line winds is the one that motivates most people. And the evidence for that is in these spectra. These are normalized fluxes, but you can see these are ultraviolet spectra of quasars that are in the relatively nearby universe. You can see the emission lines. So this one's carbon-4 right there. That's silicon-4, nitrogen-5, and Lyman alpha in emission. But you can see blueward of each of the emission lines, you see these big absorption troughs here, and there. And that's the same transition that's produced in the emission line, in this case, say carbon-4. And it's between us and the quasar, and it's coming at us at about 10, 20,000 kilometers a second. So that's interpreted as an outflow coming from the quasar, driven by the quasar somehow. And just to show you what the actual spectra look like, those are normalized. They tend to be very blue, okay? So that's why I put this plot in here, just to show you that they're very blue. So the disk is pretty hot, okay? Here's another object which shows absorption, at this case possibly at 3/10 the speed of light. And this is, again, carbon-4. This is Lyman alpha here. There's the carbon-4 emission line, and you see absorption here, but that has been interpreted probably correctly as carbon-4, okay? If you look in the X-rays in the same object, you see here at around 10 keV, a little bit less than that, you see what looks like a P Cygni profile, the same sort of profile as you're seeing here, or in the earlier ones, but reversed because X-ray astronomers do the sensible thing, and they put high energy to the right, okay? And so this is coming from basically stripped, not quite completely stripped iron ions. It's the same sort of thing. It's an outflow. In this case, it is that same velocity. It's around 0.3 C. So this stuff coming out at you at that velocity, if you knew how much mass was in it, it could do a lot of damage to the galaxy. All right. All right, so now I'm going to completely switch gears from talking about feedback, and I'm not going to talk about feedback anymore, but just tell you about a new form of evidence for an outflow from a quasar, which had not ever been seen before, and it hadn't occurred to me, and apparently not to anybody else either. And this comes from looking at what are called hot dogs. Astronomers love their acronyms, right? So hot really just means warm dust, meaning it's around 1,000 Kelvin or better. And that's a dust-obscured galaxy, okay? But what you're seeing typically in these things is not actually the galaxy. You're seeing the torus around a quasar, okay? So here's an image from MIRI which is an integral field unit, but it takes both a picture and spectra. So this is a hot dust-obscured galaxy, and I'll come back to this a little later, so I'll go into more detail. And this is the spectrum that comes from that same observation, okay? And I'm going to come back to that, but let me tell you what a hot dust-obscured galaxy actually is. They were basically discovered by WISE, this all-sky survey, which had 4 infrared bands that they looked at. And what they were finding is, well, there's a bunch of objects here that are circled, which are usually some sort of quasar. And this particular one looks really red in this image. And the reason is, by definition, after they realized these things existed. So these are the 4 WISE bands. That's the shortest wavelength, and increasing as you go down here. And in the first 2 bands, it's undetected. But in the longer wavelength bands, you can see it's brighter here in the longest wavelength and not as bright there. So it's a very red spectrum in the infrared. But the temperatures of these objects are high, meaning looks like it's around 1,000 degrees or so Kelvin. So it's a hot dust-obscured galaxy. And as I say, you can't see it in the 2 WISE bands. You don't see it in the optical, the UV, unless you really look at really deep. Okay, so that's what a hot dog is. Actually, if you look at them a little closer, they start to look a little bit like little red dots, but they're just much more luminous objects. Yeah.
The red dots are redshift.
Well, but they're called red because they have a V-shaped spectrum, right? They're sort of blue in the optical, and they're red in the longer wavelengths in the optical. These things are blue, it turns out, in the optical and the UV, and they're red but the break is at around a micron, not at near the Balmer break. So in that sense, they're different. And the LRDs are probably not dust obscured. They don't seem to show much long wavelength, meaning several microns. So here's a bunch of spectra. So I always showed you a spectrum of something like this. That's a quasar spectrum. That's Lyman alpha. There's carbon 4. Okay. And as I said, they're blue. This is nu L nu, which is a sensible way to plot these things. I got to put in the propaganda for the theorists, right? You can tell where the energy is coming out. That's the nice thing about it. Now, they are like little red dots in the sense that they're blue in the optical, but at a micron, they start to turn red, okay? This green one is what's called a quasar-2. So I should say this is H beta and H alpha. So a quasar-2, you still see a broad H alpha, or sometimes it's not broad, but if you look in polarized light, you'll see it. This is the same thing's true of Seyferts, right? But they're highly dust reddened, which is why they drop down here instead of continuing on up the way these are. But you can see in both of these objects, the blue, well, you can have a hard time seeing it, but there's a bump out here around 10-ish microns. In the green one here, you see the same sort of thing. You see about typically a third of the emission, bolometric emission, is coming out in the mid-infrared. And that's just reprocessed ultraviolet light. This hits a bunch of dust grains, it bounced around for a while, and it comes out as mid-infrared radiation. Okay. This is a theoretician's torus model, so you can ignore that. But the hot dogs are all these sort of red curves. And they're called that because they tend to peak at a shorter wavelength than a typical quasar bump here. The quasar bumps are typically, like I say, around 10. These things are often shorter than that, a few microns. So they're hotter dust. They also tend to be very luminous. And you can see here, they're much more obscured than a quasar-2, right? There's very little emission here at 1 micron and longer. But in fact, if you look at these things carefully, you do see some infrared and ultraviolet emission. I'll show you that in the spectrum next, okay? Okay, so here's the SED for this object I'm talking about. It's W2246. Depending on who you talk to, the people who've been doing this work like to say it's the most luminous quasar we know about in the universe. It's 10 to the 48 ergs a second. It's not lensed, so it really is intrinsically really bright. And you can see here, so these are, that's the spectrum I was just showing you, the MIRI spectrum. These are ground-based optical and UV spectra. So you can see there's Lyman alpha, carbon 40. So you see all these broad emission lines. But you can see the bulk of the luminosity is out here, okay? Maybe around 20 microns, something like. These are photometric points from, well, various places, Herschel and et cetera, okay? Now what's interesting about this is still sort of blue, kind of flattish, but it's not red. But you can see the luminosity here, this is, like I said, it's 10 to the 48 ergs a second, bolometric. This is a wimpy 10 to the 45 ergs a second, right? So it would be a quasar if you just saw it that way. But it was discovered in the infrared. All right. Now, if you look at those spectra from the optical or the UV that I showed you, you do see very broad emission lines. So this sort of, I don't know what color that is, pinkish orangish line is the oxygen 3 line. So the usual narrow line region emission, but it ain't narrow. It goes out to 10,000 kilometers a second, okay? Carbon 4 looks similar, okay? Similar width. There does seem to be possibly a bit of absorption here. It's not clear, but I'll come back to that. And then here's H alpha and H beta. Okay, so they're all broad and pretty luminous. Meaning, you know, they're 1% of 10 to the 45 ergs a second. So going back to this image then, so this is the MIRI spectrum. I was just describing this earlier. In fact, this source is a redshift of 4.6, and these other objects around here are actually at the same redshift, and they're within, you know, 40, 50 kiloparsecs or less. So it looks like an ongoing merger type system. In fact, if you look at this with ALMA, you can see gas streamers connecting all these galaxies. So it's becoming at least a group, maybe a cluster, okay? And in the meantime, this thing's accreting at about 100 solar masses a year, the black hole, to give you the 10 to the 46 ergs a second. It's also producing stars that's probably 500 or 600 solar masses a year. So if there's feedback affecting the galaxy, it's not doing a hell of a lot of damage. I mean, 400 or 500 solar masses a year is a lot of star formation, maybe 600. Okay. This thing's just a foreground galaxy, which happens to fall in the way they've made these colors. That's mostly PAH emission from that galaxy. So that was pretty cool. Now the feature I'm going to draw your attention to is this thing right here, which you can see, well, this is, as I said, a redshift of 4.6. So the rest wavelength is right around 3.4 microns. All right, so if you do zoom in on that a bit and take out the continuum, this is what it looks like, okay? And you can see it's between 3.3 or 3.2 and sort of 3.5 microns. Now this is actually a well-known feature in the Milky Way. If you look towards O stars in this wavelength range, you will see this feature. And it's coming from both aliphatic and aromatic carbon molecules. And we're not sure if they're free-floating or if they're on the mantle of dust grains. They could be either. They're intrinsically fairly broad. You can see there's a few individual features right there. You can see there's one here and there's another one there. This one's an aromatic feature. The rest of these are aliphatic. Aliphatic just means linear chains of carbon. You also see them in absorption towards nearby type 2 Seyfert galaxies. So they're very common. And then when Spitzer started doing a lot of this, people realized that if you see a very red infrared spectrum with this absorption feature, it is an AGN. People couldn't tell originally with Spitzer, was it an AGN or was it a starburst? This feature, when you see very steep, you know, red spectra with this absorption feature, you always see X-rays or you see other features of AGN. So it is the signature of an AGN. So that's been known for 20 years or so. What's interesting as well, these are Spitzer. I think this one's a Spitzer spectrum. The signal to noise is not great, okay? You can see in this case it's an emission, that 3.3, that's 3.3 microns. Sometimes you see it in emission, sometimes you see it in absorption. The 3.4 micron one is almost always in absorption if there's a bright infrared source. Sometimes you can see it in emission, but if it's not against a bright infrared source. Okay, all right. So here I'm just comparing to, this is a spectrum towards an O star in the Milky Way. Now, of course, these are dust people, so they plot things backwards, right? I could have turned the thing over, but I didn't. Okay, you have to do that in your eye. So these are two different fits, one from Chiar, that's the blue one, and then one from Drain and Brandon, I'm spacing on his name, another dust person. They love these things. So they're trying to figure out where these things are, what they're made of, et cetera. Okay. Hensley, Brandon Hensley, there we go. Help myself with the quote on there. So these are the different individual features here that they're fitting these things with. And these you can see in the lab, right? That's where the information's coming from. All right, so what we're seeing is that exact same set of features. And here's a fit from Andre, just fitting Gaussians to this, using the same wavelengths as you have for the Milky Way. Okay. And the thing is, again, this is a very bright source. It's also been seen with ALMA. So you can get the redshift really well with ALMA, either from C+ lines or various other lines. So now you know the redshift really well. But if you look at these features, it turns out they're all blue shifted by a little over 5,000 kilometers a second. All right? So what that's telling you is that there's dust between us and the quasar. That doesn't surprise you because it's a hot, dust-obscured galaxy. But some of these grains, either individual molecule-type grains or probably more likely the mantle on a bigger silicate grain, is moving at us at 5,000 kilometers a second, which is kind of surprising because these are dust grains, right? If something's going 5,000 kilometers a second, you'd think there should have been some shocks or something like that around and you get rid of the grains. But apparently that's not true. Okay? So again, this is sort of what is a PAH. Well, these things aren't, you have to be careful with the terminology here. If you talk to dust people, they don't like to call these things PAHs. But that's what they are, okay? They're either, these are aromatic when you see these, carbon things look like benzene rings. And these more linear chains here, they produce these aliphatic features. They're slightly different in wavelength. But they're basically either bending or stretching of these bonds that produce these absorption features. Or emission. If you hit them with the ultraviolet photon, they'll produce emission at these same wavelengths. Okay. All right, so here's what Andre gets from fitting that. The rest wavelength we know. You can measure the optical depth, and you can measure the widths. The widths are not a measure of any velocity or anything like that. It's just the intrinsic width of these molecular features. They're fairly broad. They're typically 1,000 or a couple thousand kilometers a second wide. So they're not like atomic transitions where they're really narrow, which is one of the reasons why I think people haven't noticed that these things are probably blue shifted if you look at them in nearby galaxies. But if you assume roughly solar metallicity for this gas, and assume that the gas-to-dust ratio is like it is in the Milky Way, you can actually work out a column. Now, probably this object from both the spectra that you see in the optical and the UV and from ALMA is roughly solar, maybe slightly supersolar metallicity. It's a pretty big galaxy. It's 10 to the 11 solar masses worth of stars. It's big in mass, but it's a very compact galaxy. All that mass is crammed within about a kiloparsec, a little more than a kiloparsec. So it's very dense. But the column that you get out is pretty substantial, 4 by 10 to the 22, or in grams per square centimeter, it's maybe a tenth, okay? Now, on the other hand, this object, while it's really luminous, has not been detected in X-rays. So it's got to have a really big column if it's got a normal X-ray luminosity. It's probably, if you look at the ALMA estimates, it's at least 10 to the 24, probably more like closer to 10 to 25, and that's consistent with the lack of X-ray detections. So there is, I'm not sure if they've secured time, but they certainly proposed to point at this thing with Chandra some more. Yeah.
Have they looked in the catalog?
Yes. Oh, yes. They stacked everything in the catalog. But if they stack it, you don't see any, well, you always see some X-ray photons because they're just around. But yeah.
Well, but one can go to high-energy X-rays or gamma rays.
You could.
Yeah.
Yeah. Yeah.
Norm, do you see anything at lower radio frequencies, gigahertzes, and VLAS or something?
Well, let's see. I showed you that there are some detections in the radio. I'm not sure how far out that went, actually. I showed you the SED, right? So, no, I think that's still sort of,
Yeah.
not far out. I believe the answer is there doesn't have a strong radio jet. It's not like it's radio loud quasar.
Unless there's a hockey stick, you're not going to see it.
Well, I think there is something out there. It's been detected, but it's not like it's a big booming radio source. Yeah. this. All right, so now, given that we know the column is much bigger than 10 to the 22, right? The column in this outflow is not real big. But to me, it's very suggestive that this is about 1/10 of a gram. This is just from fitting a slab model, right? You know what the optical depth is. You think you know what the opacity is for each one of these features. And if you use the normal gas to dust ratio, then you get this column, okay? And that to me is very suggestive. These features are fairly, they're 1/10 or a little less than 1/10, right? And this one's only 2%. You know, if the outflow had more mass loss in it, you'd see a deeper feature in these 3.4 micron. And you don't, okay? But if you just assume that, you know, the silicate grains, the bigger grains, or the bigger carbonaceous grains, are also there in the same abundance, then this will translate to an optical depth in the continuum at, you know, a micron out to 10 or 100 microns of order unity. Okay, so that, if you got a wind which has an optical depth that's of order unity, you think, okay, that sounds like radiation driving, because that's where you launch winds from, is roughly optical depth unity. So if you just assume that's the case, so I just go through some of the calculations, right? The optical depth that you see at 3.4 microns is the opacity at 3.4 microns. We're just using the values from the Milky Way, okay, or from where else do you know these things, right? So that's how you figure out what sigma is. Okay, that's the opacity. Now, if you pick some number like 10 parsecs, and I'm picking that number because that's roughly the dust sublimation radius, it's about 5 parsecs. Then that gives you the density, so that's some rough estimate of the density that you're seeing. And then the optical depth to actual dust, if you assume, again, a normal gas to dust ratio and normal opacity for the dust grains, it's, like I say, it's of order unity. Okay, yeah?
Presumably there will be free electrons. And Thomson opacity is not much less than that.
It's very similar. There's not that many free electrons in this gas.
How do you know?
It's very high density, and there's very little UV hitting it.
But maybe energetic particles, we don't know.
Oh, well, there certainly are energetic particles. No, but if you look at the ALMA, now it's hard to tell exactly where you're looking with ALMA, but towards, as best you can, towards the center. It's basically, it's molecular gas. This is all molecular gas. Yeah, yeah.
So you don't think Thomson opacity plays a role?
Not for the dusty outflow. The other outflow I showed you where you see the O3, it could well play a role there. But even there, I suspect there are dust grains still. And then the dust has a much higher opacity. So in that ionized outflow, the O3 is ionized, right? And H alpha and H beta. They're neutral, but only briefly. That may well be driven by hot gas hitting it. Okay? Although you don't see any X-rays, there is going to be hot gas coming out of this thing. So either one could be driving that. I don't think the hot gas can be driving this molecular gas. And I'll come back to that.
And the other question is, sometimes in stars you have line-driven winds.
Yes.
It's not continuum. So how do you know that atomic transitions do not play a role?
You don't see them in absorption. So if you don't, and there's very little UV. I mean, it's only 10 to 45 ergs a second, but that light's almost certainly scattered. It's not directly coming through the torus to our line of sight. Now you know that in some of these objects because we have gone back and gotten polarimetry, and that blue light is polarized. So what you're, well, I think I have a picture. I'll come back to that. Yeah. So yes, in the paper I go through this calculation of how much of the UV is going to be driving this, and it's negligible compared to just the mid-infrared, just because there's so much more mid-infrared photons in this along our line of sight. If you're looking down the hole in the torus, yeah, then it's all UV. Okay, all right, I said that. All right, so now you can just try to calculate what are the various accelerations on this gas. And so I'm not going to talk about the UV one here, but it turns out to be, like I say, about 10% of this. Okay, and it's assuming that there are dust grains there. If it's just electron scattering, it's a factor of 20 or so, 30. Okay, so that's just the radiation force, which is basically just the bolometric luminosity divided by C, and then whatever's coming out in the mid-infrared. And then the mass is, 4 pi r squared times the column density. This up here is the optical depth times the column density, so the column density drops out when you calculate the acceleration. So the acceleration is about 10 to the minus 2 centimeters per second squared. Okay, this is at 10 parsecs. Well, that's a small number, actually, right? The acceleration in this room is 10 to the 3 centimeters per second squared, 980.
This is a million times bigger than acceleration in galaxies.
It is big for a galaxy, but it's pretty gentle, which is why I like it, right? I mean, these dust grains are being sort of slowly, yes, galaxies. Like if you stepped out in the galaxy, you wouldn't notice any gravity at all. But you wouldn't either here, right? I mean, if you were pulled down with 1/10,000th or 100,000th, you'd say you were weightless, right? So it's very low. From the black hole, it's also, it's about, 10 times lower, 20 times lower. So this thing's super Eddington because of the dust opacity. Okay, it turns out this hole is probably also just super Eddington slightly, if you believe the estimates from the widths of those broad lines that I showed you. The mass of this thing is probably a few by 10 to the 9 solar masses, but it's 10 to the 48 ergs a second, so it's probably like 3 or 4 times Eddington if you believe that. But it's close to Eddington. The acceleration to gravity, the circular velocity is something like 300 kilometers a second, so that's even smaller. But just to point out, right, these are both scaling like 1 over r squared. This is scaling like 1 over r because it's roughly isothermal like galaxies always are. They somehow know to do that. So what happens, of course, is that if you're close in, these two dominate. But if you go very far out, this one starts to dominate. Okay, so that's important because what it means is if you get out to about several kiloparsecs, the radiation is no longer able to push the gas out. So this one has to be launched inside of several kiloparsecs. Okay? And outside of the dust sublimation radius, because you're using the dust grains to push it out. So somewhere between, say, 5 parsecs and 5 kiloparsecs. All right. Now, but of course, the acceleration is dropping off like 1 over r squared. And the velocity that you reach is basically the radius times the acceleration, the square root of that, which I think I show in the next one here. Yeah? Okay. So here's the velocity, if you ignore the velocity from the galaxy, because at first you don't have to worry about it. So here's your electron scattering opacity, dust opacity that we were asking about earlier. Okay. And then 1 over gamma. The gamma is just the Eddington ratio. In this case, gamma looks like it's maybe slightly bigger than 1. But this number is a lot less than 1. So as long as this number is less than 1, you're going to have a positive outflow just from the pushing on the dust grains. Okay? Now, this is the bolometric luminosity. That's the launch radius. If you just say, well, the launch radius is the sublimation radius, which is going to be pretty close probably. Okay? That goes like, the luminosity over the temperature to the 4th power. So what that means is that R0 is scaling like the luminosity to the 1/2 power. And the velocity then is scaling like the luminosity to the 1/4 power. So that's the signature of this wind if you go look in lower luminosity objects. So that is one of the things we're applying for JWST time, to look at lower luminosity objects to see if we can see the same outflow feature and see if the velocity scales that way. All right. Now, if you include the galactic potential, then instead of just this, you get this term which is logarithmic in the radius. But it turns out, right, when you get out to 5 kiloparsecs, this term, is bigger than 1, and so, you can't launch a wind out there. It also means that the velocity slows down once you reach out there. So here's just a plot of the velocity as a function of radius for different launch radii, and I've zoomed in here. Oops, sorry. So that you can see what's going on. If you launch at 50 parsecs, you only get up to a couple thousand kilometers a second. This is where the normal, just the Gaussian fitting gives you 5,000 kilometers a second. I think this one's actually more accurate. So this is one where you launch at, in this case, exactly 10, twice the dust sublimation radius, and you reach about 10,000 kilometers a second. But if you keep following it out, it actually does turn over and decrease. Okay, it'll slow down. Okay, so now what I want to do is a little bit of line radiative transfer in this wind.
There is also the issue of snowflow effect, because the outflowing gas
Runs into things.
runs into and
Oh,
then
yeah.
gets slowed down. So you didn't put that in.
I did not put that in there.
And so what?
So I was saying I'm ignoring feedback for now.
Not feedback, but
Well,
matter.
that would be feedback, yeah, sure. No, that's right.
Yeah.
It will. But on the other hand, if you're going 10,000 kilometers a second, you will slow down, but you have to get 10 times your mass before you slow down to 1,000 kilometers a second, so you're still going to be going out. Yeah. And there is a lot of matter to run into, for sure, because we see that in the gas. You see that from the ALMA observations. So yes, you have to worry about that. So what I want to do, though, is just go through the radius of transfer. So the optical depth, you know, the usual way it's modeled is just as a Gaussian, right? So there's the opacity, which depends on the line you're looking at. The J just means one of those 5 transitions I was talking about. That's the wavelength. And this is normally, you know, we'll fit it with a Gaussian. But there is a Doppler shift, right, from the velocity, from the outflow. And I'm just going to show you plots where I've just assumed you're looking right down the pipe. I'm not worried about, you know, winds that are going at an angle to your line of sight, because this is a first go around, right? So I'm just going to fit this and see what you would need to have, okay? So here's what the line profiles look like for what turns out to be the best fit I could get anyway, to get the optical depths that are observed. And you can see a lot of them are pretty flat topped, and the reason for that is because the intrinsic line width is pretty broad, okay? Unless you're really moving in a hurry, you're going to get a flat top as a result of that. This is plotting it the way the dust observers do. Tau goes up instead of down, okay? And I'm just comparing the line profile I got to one from the Milky Way, okay? And then I'm going to show you what it looks like when you try to fit it to the model, to the observations. And this is Monte Carlo by hand. I just kept adjusting things, right? So we'll do a Monte Carlo really soon, but not yet. And you can get a decent fit to the profile there. You can see the individual components. But this thing is actually moving. So this is being launched, as I said, at 10 parsecs. And I'm assuming it's been on for 1 million years, because, of course, it takes a while to get out there. And I'm also assuming, as Avi was pointing out, that it's not running into anything, okay? All right, so you get a pretty good fit that way. But when you do that, you know, the velocity that this thing actually, the terminal velocity is 10,000 kilometers a second. But, so then, you know, again, assuming it's just a smooth, continuous flow that's not clumpy, this is what the column density looks like, as you know, looking in from the outside, or this is looking from the inside out. It's around a quarter, okay? And there's the density's a bit higher than I had quoted from that slab model at the launch radius. And the mass loss rate then is about 600 solar masses a year, which is higher than the accretion rate onto the hole, but it's just comparable to the star formation rate. Okay, so the feedback, if you believe this story, is sort of marginal, right? You'll reduce this star formation that you would have had by a factor of 2. On the other hand, you reduce the mass that you accrete onto the hole by a factor of 6. So it's really preventing the hole from getting a lot of matter. Okay. All right, then now this thing, this is showing the optical depth then. And the optical depth unity surface, you know, is outside the dust sublimation radius in this particular model. So that seems reasonable. And the temperature at optical depth of 3/4 is just over 1,000, which is consistent with what you see in the SED. All right? So that all seems like a consistent story. All right. All right, now you might ask, how long is this wind going to last? You're losing 600 solar masses a year. You know, how much mass is there in the torus? Because that's the source of your material. So you can try to estimate that, you know, if you're below optical depth unity, so tau is bigger than 1, below meaning towards the black hole, then, of course, you don't expect a wind to be launched from those regions, because there's nearly as much radiation coming back at you from the stuff above you as there is from the stuff below you. And you get, you know, you can get a hydrostatic equilibrium using radiation pressure. Now, it turns out that the temperature gradient is superadiabatic, so you expect it to be convective. The radiation pressure totally dominates over the gas pressure. Like you can see here, it's just crazy, much higher than the gas pressure, all right? So it's, you know, it's like a big O star, except it's not an O star, the temperature is only 1,000 degrees, so it's like an M star or whatever, right? All right. So, you know, given that, since it's a superadiabatic temperature gradient from the radiation, you figure, okay, fine, it's going to be convective. That means the entropy is roughly constant. So that tells you how the temperature and the density change. The density goes like 1 over r cubed. So then you can just work out the mass if you just integrate down to the dust sublimation radius. It's around 10 to the 8 solar masses. So this thing's losing mass at not quite 1,000 solar masses a year. So you only last 10 to the 5 years this way. So I don't think it only lives that long. I think what's going on is that you know there's 600 solar masses of gas coming in to feed the stars. The stars take a long time to eat the gas, so that gas keeps coming in. It's going into the torus, but when it gets into the torus, it's then being ejected. Some of it, 100 solar masses a year, is still going all the way down to the hole. Okay, so this thing lasts at least 10 to 5 years, but probably a lot longer than that. I mean, the gas mass out to a couple kiloparsecs is nearly 10 to the, well, it is 10 to the 11. So that would feed it for quite a while. On the other hand, this hole's already, like I said, several times, it's like 5 or 4 by 10 to the 9. So you don't want to feed it too long. If you feed it 50 million years at Eddington, it's going to be, it's going to get to be a really big hole. Well, maybe it is. Maybe it's the center of a, 10 to 15 solar mass cluster, when it could be 10 to the 10 or even bigger. All right, so it doesn't seem crazy. So the conclusions of all this are the following. So first of all, these observations of these hot dogs show these very steeply rising mid-infrared spectra. And they do show this 3.4 micron absorption feature, which is, I say classic because it's 20 years old now, AGN signature from Spitzer. Okay. What's new is with JWST, because you have a much higher signal to noise and much better, well, pretty good spectral resolution. Spitzer was okay. You can actually see that it's blue shifted. Now, part of that was because you have better spectra, better instruments. But the other reason is because this thing's a really crazy luminous object and the velocity is really high, 10,000 kilometers a second. If the scaling that I told you is correct, if you look at a quasar, it's 100 times less luminous. The velocity is a factor of 3 smaller. That's still 3,000 kilometers a second, which is maybe 2 or 3 times the line width. So that, if you had decent signal to noise, you should be able to see that. If you look at a nearby Seyfert, they're only 10 to the 44 ergs a second. Well, then it's like, not even 1,000 kilometers a second. But, if you have good enough spectra, you should be able to see that. So we're going to try to do that as well. Okay. Now, the launch radius we've inferred is about 10 parsecs to get the right line profile. And that is outside the dust sublimation radius, so that's a good thing. If it was inside, you'd be worried. Okay. The velocity is measured pretty directly. If you fit the Gaussians the way Andre did, you get 5,000. If you fit it the way I did, you get 10,000. So you know it within a factor of 2. The column is well measured because you see the optical depths, assuming a normal gas-to-dust ratio, okay, which I think is probably okay. I mean, basically, right, what is the gas-to-dust ratio? We know what the metallicity in the Milky Way is. It's 2%. Half of that is in dust grains. So that gives you the 100-to-1 gas-to-dust ratio. In any galaxy, in the ISM, half the metals are going to be in dust grains. It's just like, that's what happens to metals in gas, right? Now, you got to have some place where it's fairly high density, like the surface of a star or something like that. But, stars do produce dust grains. So does supernova, apparently. It's not so obvious how. Okay, so that seems okay to me. As I said, from the line profile fitting, it's 10,000 kilometers a second, which is consistent with that launch radius. The mass loss rate is comparable to the star formation rate and 5 or 6 times the accretion rate onto the black hole. So in that sense, it is feedback, preventive feedback as far as the black hole is concerned. It doesn't seem to be very effective feedback for stopping the star formation. But, well, Andre spent the last several years trying to look for the effect of these outflows on the host galaxy. You do see very high turbulent velocities, I got to say. Like all of the velocities in the molecular gas are 400 or 500 kilometers a second, which is going to suppress star formation. Okay. It is consistent with radiation driving on dust grains. I've tried to make sense of whether you could do this with hot gas leaking through the torus. I don't see an easy way to do it. On the other hand, I showed you those the ionized lines. That gas probably is driven, possibly by radiation pressure on either dust grains or electrons, probably dust grains. But it could also be driven out by ram pressure by hot gas. And I haven't gone into why that is, but I can just quickly say the reason is because you see it's really luminous in O3. So you've got to have a high number density of O3 to get that kind of luminosity. And one way to do that is to have hot, shocked gas from, for example, a broad absorption line wind to compress the cold gas to keep it at a high density. So I think you do need a very hot wind, and then if you have a hot wind, it's not crazy to think that that's driving that ionized outflow, or some combination of the ram pressure plus the dust, radiation pressure on the dust grains. Okay, and then as I said, you do see ongoing star formation at a pretty high level, 600 solar masses a year. So the feedback is on the galaxy is not currently overwhelming. And I guess I'll stop there.
You said something about a lifetime of 10 to the 5 years.
Yeah.
Lifetime of what?
So all I was calculating there was I know the mass loss rate, I think. And I tried to estimate the mass in the torus, which is where the flow is coming from, because it's at the sublimation radius. You don't see much UV, so you know there's a torus. So how much mass is there in that torus? So I tried to estimate that. And so that was like 10 to the 8 solar masses. Maybe, that's probably known. I mean, there's plus or minus a factor of 10, maybe.
Like a depletion time.
It's a depletion time, yeah.
So then, but that seems so short.
It is very short.
There must be a huge number of these things if you could find one.
Well, there are a fair number of really bright, really luminous quasars are hot dogs. Like, depending on who you talk to, it's like half of things over 10 to the 47 ergs a second are hot dogs. Yeah. So there is a fair number of them. Now, I think that lifetime estimate is an underestimate for the reason I said, right? There's plenty of gas farther out in the galaxy. And we know, right, galaxies are accretion disks, at least disk galaxies are accretion disks, right? Gas is coming through the disk. Some of it turns into stars on the way. It cleverly arranges it so it doesn't all end up in the center, because we don't see, really massive holes. And this is a possible way of doing that. But there is mass coming in, so you can replenish that reservoir of gas in the torus. So it could have a longer lifetime than I said. I think it probably does. I think all nearby Seyferts have these outflows like this, and they're being fed through accretion through the disk, and then they're getting into the torus, and then they're being expelled. I think is what's going on.
So one missing component in this description is how come there is star formation? Because obviously the Jeans mass, if you were to calculate Born or Ebert mass, would be huge. Like you can't make a star under these circumstances. So one way to
except it's turbulent, so you get shocks. So you get very high
yeah,
density
but still,
clumps.
the temperatures are so high.
No, it's all molecular gas. The temperatures are really low.
How low?
20, 30, 40 Kelvin.
Really?
Yes.
And how do you keep
You see that directly from the ALMA observations.
How do you keep it so low?
It's very dense, so it cools rapidly.
I see, because I was thinking about the geometric factor, so eventually this outflow runs into something and gets stopped, so the rest of the galaxy where the star formation takes place is protected from.
Yes.
So, but you're saying so is that a possible explanation?
Yes.
I see.
I think it's sort of like making an O-star, right? O-stars, you have things that are Eddington, and they should blow away all the gas, but they don't because there's a very dense layer of gas in the disk that keeps coming in.
Right.
And this is the same sort of thing, I think. That yes, you blow away a lot of the gas that's above and below the disk, but you can't get rid of the disk, right? So yes, I think it's protected.
Do you think there are TDEs here or not?
Oh, there certainly would be.
Part of the fueling, stars being disrupted.
100 solar masses a year, that's a lot of stars. You got to scatter into the center.
Well, there are a lot of stars being.
Well, there's 10 to the 11 of them out at a kiloparsec. And you got to feed 100 of them into, sub-parsec scales.
Within a year, yeah.
Yeah, within a year. That seems to me like I'd rather have dissipation than scattering to drive this thing. And dissipation from gas is there, right? Yeah.
So I think the calculation of the velocity assumes that the dust and gas are coupled. And
You assume the gas in the dust are coupled, yes.
Is there a possibility that it's not coupled and the dust only gets adjusted to that?
It is possible in some objects. The thing is, we know the densities are really high, again, in the disk of the galaxy. They're very high. from the ALMA observations. In the torus, I don't think we know directly what the densities are. You saw the estimate, assuming the gas and dust are coupled together, is it's like 10 minus 18 or something grams per cubic centimeter. So that's a very high density. It's like 10 to the 6 number density, right? So anything like that kind of density, the gas really is coupled really well to the dust grains. Now I think there are objects where that's not true, and you actually just blow dust grains out without blowing gas out. You can ask Pepe about that. We've never actually finally written that up. But yeah, I think that does happen. But in these situations, there's a lot of gas around, very high gas densities. Yeah, and that again, you have really strong evidence of that from the ALMA observations. You can just you can measure line ratios to get gas densities, and they're typically 10 to the 3, 10 to the 4 or higher. The resolution is not great. I mean, it's a tenth of an arc second, but this thing's at redshift 4.6. So you're talking about maybe just a little better than a kiloparsec, but the densities are really high inside of there. Yeah.
Do you have any, either for this object or any object, like an idea of how spatially extended this kind of outflow might be?
Well, this was Abby's question. Currently, the answer is no. I mean, I shouldn't say that. In this object, the pixel for JWST is basically a kiloparsec, right? So the flow it's not, you don't see obvious signs of it out beyond the kiloparsec. You do see these high turbulent velocities, but you don't know that that's from the outflow causing trouble. So the answer is, at the moment, I would say we don't have a good feeling for that. In other objects where that Andre's been looking at, where you do have better spatial resolution, you can actually see the wind propagating out. This is not hot dogs, these are more ordinary quasars. You do see the winds propagating out to 10-ish kiloparsecs, and you can see it disturbing the disk along the way. So those objects are presumably more evolved than this one. In other words, you see a blue quasar, so you've blown away a fair fraction of the torus, so you can see directly into the disk.
And that's in the dust phase, the
Say
10
again?
kiloparsec side. Was this with kind of dust absorption?
No, you see it. No, not with dust absorption. You see it with, the usual sorts of lines that people track.
Yeah.
Yeah.
But that's what I'm kind of wondering, is whether it is just the dust outflow is just very localized. But you see
It could
hot
be.
wind further
The answer
out.
is it could be. Yeah. You don't know.
Yeah.
Yeah. On the other hand, it's not going to stay localized for that long, because like I say, there's a fair amount of mass in this thing. It's going 10,000 kilometers a second. You got to run it at 10 times your mass, and you're still going 1,000 kilometers a second, right? Now, if you do that, I would be surprised if the dust, well, maybe the dust grains could survive that. They're going to have a lot of shocks, and that's going to disrupt the dust grains, probably. Yeah.
So related to that question and Avi's question, I guess, there's more and more evidence now that in redshift 0, AGN feedback is really important, and these halos get cleared out, and star formation quenches and everything. And presumably this would be a great candidate for a redshift 0 depleted halo.
Yes.
So what is this delay? When would it eventually happen?
Yeah, right. So I don't have an answer to that, right? Because you have to know, again, what the geometries look like, what's the distribution of gas in the halo. I mean, they're sort of isothermal, the halos, the gas halos, and people use these beta laws or whatever they call them. They're not so far off of isothermal. So there's plenty of gas out in the halo today, and I would guess, now these objects, like I said, this is an ongoing merger with some pretty big galaxies, right? So and you can see in some cases the tidal tails from the gas. So there's plenty of gas being deposited in the halo. And when this thing runs into that gas, well, what happens? Is it going to push it out? I kind of doubt it, because if this thing, if this is 4.6 and the galaxy is already 10 to 11 solar masses of stars, this is some BCG, right, today. And BCGs are sitting in pretty big halos, and those halos have essentially all their baryons in them, right? These big clusters have all the baryons you see. So they never got rid of their baryons. They heated them up somehow, and this could be helping with that. So the answer is, I don't know that it's going to clear out the halo that it's sitting in. And there's a really good argument that it won't, which, well, if you consider what I just said, a good argument. It's answer analysis, right? If it got that big, we know it's got all its baryons, right? So it didn't clear it out.